Synthesis is complete, and now we have a netlist. Every gate has been defined, and every connection has been listed. But there is still no physical structure. Like a recipe you read while cooking, the ingredients and steps are written, but there is no cooked meal in front of you. Now it is time to cook. The place and route process takes this recipe and physically inscribes it onto silicon. It positions every gate in its exact location. It routes every wire through real metal layers. After this step, the ghost transforms into a physical object. The FPGA silicon surface is a grid. Hundreds of thousands of configurable logic blocks, CLBs, arranged in rows and columns. Each CLB contains a few LUTs, a few flip-flops, and a few multiplexers. In the placement stage, Vivado decides exactly which cell on this grid every single netlist gate will occupy. Of course, this placement is not random. Vivado places heavily connected gates closer to each other. The Axiom stream parser gates cluster together. The BRAM controller is placed beside the BRAM blocks. The DSP RISC engine is arranged around the DSP slices. Proximity means short wire, and short wire means low latency. Think of a city planner working over an empty plot of land. The hospital is placed near the emergency services because the distance between them saves lives. The school is positioned beside the park because children will walk there. The factory is moved to the industrial zone because noise and traffic must be manageable. Every decision is an optimization. Vivado's placement algorithm is exactly that. Now we can say placement is done, and now the physical connections between every gate must be drawn. That's mean routing. Inside the FPGA, there are numerous metal routing channels, horizontal and vertical channels, different metal layers, and the switch matrix, the junctions that connect these channels to each other. Think of this like a city's water pipe network. Water must reach every building, but pipe capacity is limited. Two pipes cannot share the same space. Routes must not clash. Vivado's router searches for and finds the shortest, least congested path for every connection. Millions of connections and millions of decisions happening simultaneously. When routing is complete, the FPGA grid is no longer empty. Every cell is occupied. Every wire is pulled. Every connection passes through a physical metal path. The ghost now exists on silicon as coordinates, metal layers, and switch points. In synthesis, we had met the timing constraints. The critical path was 3.84 nanoseconds. But synthesis used estimated delays. The wires were not yet physical. After place and route is complete, the real wire lengths become known, and physics sends the bill. As the wire gets longer, delay increases. A wire estimated at 0.3 millimeters in synthesis can reach 0.7 millimeters after routing. This difference is critical for us, because we are talking about nanoseconds here. Timing closure is only possible now. Think of a pilot who made a perfect landing in a flight simulator. The simulator was nearly ideal. No turbulence, no wind, no friction. In the real aircraft, physics takes over. The pilot faces the possibility of encountering strong winds and lightning. Post-PNR timing closure is exactly that. No longer estimated. Real metal, real length, real delay. Slack is positive 0.03 nanoseconds. This means the design meets the 250 MHz target, but this margin is extremely narrow, meaning any change or addition we make to the design could push this slack below zero. We examined the critical path in Vivado. The source of the longest delay, the data path between the BRAM controller and the DSP RISC engine. These two blocks have not been placed close enough to each other. Solution: a Pblock constraint. We tell Vivado to confine these two modules to a specific region of silicon. Physical proximity is enforced. The wire shortens and the delay drops. Pblock constraint added. Route and timing summary refresh. Critical path 3.81 nanoseconds. Slack positive 0.19 nanoseconds. The 250 MHz target is met, accounting for physical delays. This time it is real. This time physics confirms it. Look at the floor plan. This is the ghost's silicon portrait. Every module in its own region, every connection optimized, every wire at minimum length. Top left, the Axiom stream parser, receiving network packets. Center, the BRAM controller. holding the order book. Right, the DSP risk engine, computing risk within nanoseconds. Bottom corner, the fixed generator, firing the order. Inside every square of this grid, something is alive. Every LUT making a decision, every flip-flop holding a state, every wire carrying a signal. All of this simultaneously, within the same clock cycle, deterministically. This is no longer code, this is silicon. Look at a satellite photograph of a city. Every district carries a function. Every road enables a flow. The city works exactly as it was planned. The Ghost's floor plan is exactly that. On silicon, every gate in place, every wire pulled, and every signal on its path. This physical design is converted into a single configuration file that will program every LUT, every switch point, and every connection on the FPGA, and the Ghost awakens on real hardware for the first time. This is Axiom Tech, and I am Epoch. I will see you in reality.